Okay, Assalamualaikum. So we continue with chapter number 3. So here we want to see the probability of the where is the next monomer will do the bond with the current monomer. Okay, so here is this is from our PDA, I believe so. So it's a simplified model of a random chain in one dimension. Okay. So each segment can point in only two possible directions, right or left. Okay. So it can be either in the right position or in the left position of the current monomer. So if we see that a chain of n segment end at a position x, then we know that the next chain, n minus 1 segment leading up to this point must have terminated at either x plus l, okay, more than current position, or x minus l less than the current position. See, so we can relate this probability Pn to probability Pn minus 1 at x minus l and Pn minus 1 at x plus l as Pn equal to 1 over 2 Pn minus 1 x minus l Pn minus 1 x plus l. So Pn minus 1 x equal to 1 over 2 l squared partial squared p over partial x squared. Okay, so this one is just the Taylor expansion. Okay, the Taylor expansion. So when we take Pn, taking this to this side, so we have Pn minus Pn minus 1x equal to 1 over 2 L squared partial to partial 2p over partial x squared. So we are going to have this the heat equation. Okay, so and solution for this heat equation from our math method or advanced math method is equal to Pnx dx equal to 1 over square root of 2 pi n L squared exponential minus x squared over 2n L squared dx. Okay, so that is the solution for this heat equation. Okay, so for 3 dimension, okay, so we have x squared plus y squared plus z squared dx dy and dz. And for spherical coordinate, okay, so r equal to r squared, this r squared 2n l squared dr. Okay, so we have this probability distribution. Okay, so we meaning that we can estimate the distribution of the monomer in one dimension. Okay, so these are 3 dimension. The previous one is 1 dimension, and these are spherical coordinate. Okay, so when where the next monomer will do the bonding with the current polymer or monomer. Okay. Okay. So next is the loop formation. Okay. So here we have the chain. For example, the polymer is a chain, so we can take the end and the initial carbon and the final carbon, so we can stick it together. Okay, so making a loop. Okay, so the molecule will form a loop when the end has a position near x, y, z equal to 0. So Pn 0, 0, 0 exponential 0 is 1. So 1 over 2 pi n L squared 3 over 2 dx dy dz. Okay, so here we can see that x, y, z equal to 0. Okay, so we have this proba. Okay, so the probability of loop formation in the ideal chain decrease as the number of segment or the segment length increase. Okay, so kalau polymer tu panjang, okay, so the probability making the loop will be much smaller. Okay, so we have a good estimate of the rate of formation of circular DNA from linear DNA. Okay, circular DNA, the loop, linear DNA is the in one dimension. Okay, so this are just like contoh, sebagai contoh adalah kereta api. Kereta api ada 100 gerabak, ada 1000 gerabak. Okey. Kalau 100 gerabak tu ataupun 10 gerabak tu mungkin cepat untuk bertemu hujung ke hujung. Tapi kalau untuk 1000 gerabak, so making the loop formation might be impossible. Okay, so next is we have a kalau polimer tu dah buat gumpalan, okay, global, so we can stretch the random coil. So how we can stretch the random coil? Okay, so we can hold the end of one end of the random coil at a fixed position, and we stretch the other end. Okay, so the molecule will have more convolution when the ends are closer together than when they are far apart. Okay, so more conjugation, macam-macam conjugation, because of this the molecular force that interact with each other. But if far apart, there will be less molecular force, so they will have less configuration. Okay, so the molecule will exert a force entropic to pull its end together. Okay, so why it try to make a smaller molecule? Because it will cost less energy. Okay, so the calculation of force, entropic force, is equal to this equation. Okay, px dx 2 pi omega n L squared exponential minus x squared over 2 n L squared dx. So where omega, capital omega, is the total number of conjugation of the chain. Okay, so we have multiply this with the probability, so we get the force. So the chain entropy, okay, the entropy S equal to K ln omega px dx, putting it here, so we have this one is 0, this is the solution. So we calculate the entropy as K ln exponential minus x squared over 2 n L squared. So the current position of the monomer. So what is the entropy of that chain? Okay, so the free energy Gx equal minus Ts, putting from the previous slide, minus Kt ln exponential minus x squared 2 nL squared. Okay, so if we expand this, okay, or we solve this ln exponential this one, so we have Ktx squared over 2 nL squared. Okay, so we can calculate the free energy using this value. Okay, so Kb, Boltzmann constant, temperature, the position, the length, and the number of monomer. Okay, so we have this free energy. Okay, so the force pulling end together is equal to Fx equal dg over dx equal to Ktx over nL squared. Okay, so these are the force that pulling the end to end together. So the conclusion for this one is that a random coil behave like a simple elastic spring. Okay, so we can panjangkan spring tu, bila kita lepas dia akan bergumpal balik. Okay, a longer random coil larger than will be looser and easier to stretch. Okay, longer random coil. So the factor 1 over n make the force smaller as the number of segment increase. Okay, the force smaller when the number number of segment increase. And restoring force increase with the temperature. So by looking at this formula, okay, when T increase, F increase. When N increase, F decrease. Okay, so next is application for the protein. Okay, so backbone rotation in protein, the secondary structure. So these are the secondary structure. So you can see that if the hydrogen bond, we cut this hydrogen bond, so then this carbon can move around or do the rotation. But if we have the hydrogen bond, then it is fixed at like this figure. Okay, so the polymer type backbone has three kind of chemical bond. So the bond between the alpha and carboxy carbon, C alpha and C prime bond. The bond between the amide nitrogen and alpha carbon, the N-C alpha bond, and the bond between the carboxy carbon and the amide nitrogen, C prime and peptide bond. So these are the three bond. Okay, so here from this picture, you see the first one is N C alpha, and this one C alpha and Cn, C prime, and also this R. Okay, alpha and carboxyl, the amide, and Cn and peptide. Okay, so amino terminus and the carboxyl terminus. Okay, C alpha C prime is dihedral angle as theta. So this one P psi, and C alpha bond dihedral angle as P. Okay, so we have these two angle. Okay, so we can see that these are the angles. So and this also the angle and C alpha. Okay, so from this angle, so we can see, or we can plot, or we can do the experiment and get the Ramachandran plot where we have the energy minima of the rotation. Okay, so we try to get the least energy for the rotation, or to the polymer or polypeptide or polymer to be stable. Okay, so here we can see here we have beta sheet, alpha helix, okay, and alpha helix. Okay, so the three energy minima is the probability of conjugation of the polymer. Okay, the rest is not probable configuration. Okay, so here for alpha helix we have P equal to minus 57 degree and psi equal to minus 47 degree. Okay, so this angle is minus 57 and minus 47. Okay, so we have the most stable beta or alpha helix. This one is for the beta. Okay, so next is the entropy of protein denaturation. This is macam kita masak telur. Okay, so kalau kita masak telur tak boleh balik, telur dadar tak boleh jadi balik telur ayam. Okay, so we see this protein denaturation. Okay, the native state of protein depend on many internal contacts between the constituent amino acid. Two general contacts are between neighboring residue in alpha helix. Distant contact between residue separated by 10 of 100 of amino acid. Okay, next each other and far from each other. Okay, so a protein cannot be partially folded, at least not for any significant amount of time. It must be either completely folded or highly disordered. Okay, completely folded meaning bergumpal, highly disordered memanjang. Okay. Okay, so these are the entropy of the protein denaturation. So we can see here, these are gumpalan, these are the straight line or the polymer in straight line, and these are the intermediate state. Okay, and this one you can see that the free gift energy is less at this native state. It's preferred for this native state. Okay, and these are the excited state. So we have this folding energy folding. Okay, so how energy protein fold? Okay, so protein folding. So the formation of a molten globule from a random coil is accompanied by a drastic reduction in number of conformation. Okay, so here we can see that a homopolymer, one polymer with 100 segments can be arranged in about 10 to the power 67 ways of a cubic lattice without having any segment. Ini macam contohnya kalau kita lah, kita tidur, banyak posisi tidur yang kita boleh buat. Okay. Okay, so macam-macam posisi kita buat. So here is 100 segment only, so we have 10 to the power 67 ways or configuration or conformation. And converting this chain to its maximum density reduce the number of combination to about 10 to the power 17. Okay, so daripada 67 ke 17. Okay, but here we can see that as we see A and B. So the protein prefer only one or two of these 10 to power of 17 possibility. Okay, dalam banyak-banyak possibility configuration, bentuk combination, we only have one or two configuration that is permanent or not permanent, the favorable for the protein. Okay, so this favorable configuration is either on and off. Okay, so we can A and open and. So the last one is these are the example of or one of the model for the protein folding. Okay, so here we have the 1, 2, 3, 4, 5, 6. Okay, so we have hydrophobic and polar molecule or polar residue. Okay, from the side chain. Okay, so if we put this into this sequence HPP HPH, okay, so we can have this one dimension, this one, this one, this one. Okay, so these are also all are or confirmation. Okay, so kalau kini kita tengok ada these six chain or this six model. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so 30 configuration. But here we can see that the minimum context measuring the minimum energy is in this position. So it can be in any configuration, but it's prefer in this configuration because it has a minimum energy. So HH contact, it will produce the minimum energy. So it will be prefer in this configuration. Okay, so that's all for this chapter number